In the last lecture, we have seen Eulerian angles, and we know that these angles can be used as generalized coordinates to fix the coordinate orientation of a rigid body with one point fixed and can be completely specified by three independent Eulerian angles, right? So in this lecture, we will see what are uh, Cayley Klein parameters. But before using the Cayley Klein parameter, we should know some basic concepts of metrics, like what is conjugate matrix, what is trace. All these are very basic concepts, but we need to revise them. Only then we would be able to understand the next concepts. Okay. So basically, what is the conjugate matrix? As the name suggests, conjugate matrix is a matrix which is obtained by taking conjugate of every element of the matrix. See, what is a conjugate matrix? A matrix which is obtained by taking a conjugate of each element, and the new matrix which is obtained is nothing but a conjugate matrix. Second, what is trace of a matrix? Trace of a matrix is a very simple term. Like if you have a n cross n matrix, that is a matrix of order n, then the elements which are present on the diagonal, that is the principal diagonal of the matrix, you have to add them. Then what you get, we call it as a trace of a matrix. For example, I have this matrix. I have this matrix. In this, the elements in the principal diagonal are 1, 11, 16, and 6. If I add them, I get 34. So for this matrix, the trace is 34. In this way, you can find the trace of matrix. In the next concept is transpose conjugate. So basically, what is transpose conjugate of a matrix? First, if I consider a matrix A, then first take its conjugate and then transpose the matrix. The matrix hence obtained is called as a transpose matrix of matrix A. Okay, so these are really basic concepts. Then after that, what we have is transpose conjugate. We are done. The next term is unitary matrix. So a matrix Q is said to be unitary if Q and like the product of the matrix with its transpose conjugate gives you identity, then the matrix Q is said to be unitary matrix. That is, a square matrix Q with complex elements is said to be unitary if the matrix with its multiplication with its conjugate matrix gives you the identity matrix. So that matrix is said to be unitary matrix. So next concept is the self-adjoint matrix. So what is a self-adjoint matrix? A self-adjoint matrix is in a linear operator. Suppose we have a matrix P. Okay, if that matrix, and if I take the adjoint of the matrix and both the matrix are same, then the matrix P is said to be self-adjoint matrix. Then the matrix P is said to be self-adjoint matrix. What is a self-adjoint matrix? If a matrix P is similar to is the same to its adjoint, then the matrix P is said to be self-adjoint. Okay, so the next term we have is Hermitian matrix. What is it? Hermitian matrix. So what is Hermitian matrix? A matrix A is said to be Hermitian if the matrix is equal to its transpose conjugate. For suppose I have a matrix A and I take its transpose conjugate and it is equal to the matrix A, then the matrix A is said to be Hermitian matrix. All this you have already studied. The next is the term which is the similar matrix. Now this is regarding two matrices. A matrix A and a matrix B is said to be similar if there exists an invertible matrix. When is a matrix inversible? Invertible when it is non-singular. If there exists a non-singular matrix P such that A is equal to P B into P inverse, then we say that the matrix A and the matrix B are nothing but similar matrices. So a matrix A and matrix B are said to be similar if there exists a non-singular matrix P such that A is equal to P, B, P inverse. Okay. So all this is basic. Now we come to a main topic, that is Cayley Klein parameter. So what are Cayley Klein parameters? See, you have already studied Euler angles, and we know that Euler angles are really important in order to like check the orientation of a rigid body which is fixed at one point. But using the Euler angles in like problems or in practice, it gets difficult because it considers or it has a lot of trigonometric quantities, so solving them becomes really tedious. At that moment I use Cayley Klein parameters. Even these parameters will help you to know the orientation of a rigid body, but these are more helpful as compared to the Euler angles. See, Euler angles are also interesting, but the thing is, it's get difficult to use them. Hence, we use the Cayley Klein parameter. See what is it written over here in your notes. Cayley Klein parameter are another set of variables which are used for the description of the rigid body with one point fix, as I said. So we know that Eulerian angles are used to describe an orientation of rigid body with one point fixed. However, it is found that the angles are difficult to use in numerical compensation because of large numbers of trigonometric functions involved. So therefore Clay and Klein like introduced to us four complex parameters. Okay, so four complex parameters, and these parameters are nothing but uh, Kelly Klein parameters. Okay, so we will study in deeply what are these, since they are saying that it is four complex parameters, right? So if there are four complex parameters, each complex parameter will have two unknown quantities, right? So in total, four complex parameters will have eight unknown quantities. That means it has like eight independent quantities. But we know that Euler angles are three, right? So basically, out of these eight parameters, we need to see that there are only three independent parameters. Okay, so we will see that in the next theorem. So see, here it is written, we will show that now these eight quantities can be reduced to only three independent quantities. Okay, so we will see that how it is reduced. And also we will see relation between Eulerian angle and the Cayley-Klein parameter. I don't think this relation would be possible for me to teach in this lecture. In the next lecture, I will tell you the relationship between Eulerian angle and the Cayley-Klein parameters. So yeah, see what is the first question. Explain how the eight quantities of Cayley-Klein parameter can be reduced to only three independent quantities to describe the orientation of the rigid body. So what we will do, I will consider a two complex plane, like a sorry, a 2D complex plane, two-dimensional plane. So consider a axis as u and the next axis as v. Okay, and a general linear transformation. You know, a linear transformation is represented by alpha x plus beta y, but in that case we have axis and y axis. But now we will consider two axes u and v in the 2D complex plane. So the linear transformation is represented by equation number 1, u dash is equals to alpha u plus beta v, v dash is equals to alpha u plus beta v. So here the matrix Q can be written as alpha, beta, gamma, and delta. So I know that this is a rotation matrix. Now these alpha, beta, gamma, and delta, these are nothing but Cayley Klein parameters. See, observe, since I have considered a complex space, so alpha, beta, gamma, and delta are complex numbers, correct? But each complex number is of the form a plus ib, so each complex number has two quantity independent quantities. So basically these will have eight quantities, but now I will show in this question that how these eight quantities are like reduced to only three independent quantities. Okay, really simple it is. See, I know that rotation matrix is unitary. I have already learned that rotation matrix is unitary. So this matrix Q is unitary. What is a unitary matrix? A unitary matrix is a matrix A. Like a matrix A is said to be unitary matrix if A into A transpose conjugate gives you identity. So I know that the matrix Q, because it is a rotation matrix, it is unitary. So Q into Q transpose or Q transpose into Q will give you identity. Correct? And moreover, I also know that the determinant of a unitary matrix is always 1. So the determinant of this matrix is 1. So how do we find the determinant? Alpha into delta minus gamma into beta, and this quantity is equal to 1. So see, we have this equation 1. What does equation 1 say? Equation 1 says that alpha into delta minus beta into gamma is equals to 1. So basically, this is the equation. Now, this equation, if I think about this matrix, so now I know that we have one constraint, because this matrix has to follow this condition, because this matrix is nothing but rotation matrix. So it has to follow this condition. So now this condition gave us one constraint, correct? Now the other constraint we will obtain by equation number 3. See, I know that Q into Q transpose conjugate will give you identity. So what is my Q matrix? Alpha, beta, gamma, delta. Now I will take this thing, transpose conjugate of the matrix. See, this star sign means it's conjugate, and we have taken the transpose. You know how do we get a transpose? Interchange rows by columns and columns by rows. So see, I have alpha beta, and over here I have alpha star beta star. Me, alpha star is the conjugate of alpha and beta star is the conjugate of beta. So alpha beta was in the first row. Now alpha star beta star is in the first column. Now here gamma delta is in the second row. Here we have in the second column. So multiplication of this will give us identity by using equation number 3. Now when you will multiply this, you will get this, and this is equal to identity. Identity matrix in of order 2 is nothing but this. See, observe the position A11 is equal to 1. The position A11 is equal to 1. So we got the first equation, and the position this A22 is equal to 1. We get the second equation, and these equation will give us the same thing. So you either take this or this. So this is equal to 0, like the position A12 is equal to 0. Hence I got the three equations when I equate both the matrices. See, we got the three equations. So now what I will do, since I have got the three equations, I got the three constraint, and the one constraint I got from equation number. See, the one constraint I have got from equation number 4. Now the next constraint I will get, one constraint I have got from equation number 4, and the next constraints I got by using this. So total constraints, how many total constraint do we got? We got in total 4 constraints. So here we notice that the first two equation in equation number 5 are real, while the third equation, see, observe, see the first equation, this equation is, let me change the color of the pointer because everything is black. Yeah. So what I was saying is the first equation in equation number 5. If you consider this equation, you will observe that alpha into alpha star, I know this is the magnitude. Alpha into alpha star will give you a real number. Beta into beta star again will give you a real number. Basically, both these equations are real quantities, and these equation can be complex quantities. So in total, I have four independent constraints. See here we notice that the first two equation and equation number 5 are real while the third is complex. Thus the equation 5 gave us four conditions, uh, and totally we have five conditions. Four conditions in equation number 5 and one condition in equation number 4. See, one condition in equation number 4 and four conditions in equation number 5. Hence I got in total how many conditions? Five conditions. I hope everything is clear. Now, in total, we had eight unknown quantities, but now we have five constraints. So, 8 minus 5 is nothing but 3. So, basically, we are left with only three independent quantities which are used to describe the orientation of a rigid body. So, half of the question we have already solved. What was the question? Explain how the eight quantities of Cayley Klein parameter can be reduced to only three independent quantities, right? But now we have to find out like few things further. See, we need to calculate also these three quantities. Now I just know that there are three independent quantities, but we need to find these quantities. So what you have to do is divide equation number 4 by alpha into gamma. Divide equation number 4 by alpha into gamma. See, where is our equation number 4? This is our equation number 4. If I divide this equation by alpha into gamma, what I will get? This side alpha will get cancelled. I will get delta upon gamma. Here gamma will get cancelled. So I will get minus beta upon alpha. And when I will take minus beta upon gamma that side, I will get this equation. Correct. So basically, what I will do, I will use divide by equation number 4. This side I will get delta upon gamma minus beta upon alpha equals to 1 upon alpha into gamma. Okay. Now what I will do from here, I will find the value, or I would say that I will from the last equation, this equation, what you can do, you can find the value of delta upon gamma and you can use it here. So how will you find the value of delta upon gamma? It is again very simple. When you will take everything here, then delta upon gamma you will get as minus alpha star upon beta star. So use this value here. So what you will get, minus alpha star upon beta star minus beta upon alpha is equals to 1 upon alpha into gamma. So now I have reached here. When you will solve everything now, you will find it really easy. So now see, we have reached here. From here now I will cross multiply and I will get minus alpha star into alpha minus beta into beta star is equals to alpha into beta star upon alpha into gamma. Alpha and alpha will get cancelled. So finally minus sign I will take there. So I will get alpha star plus beta alpha into alpha star plus beta into beta star equals to minus beta star upon gamma. Okay, but this I know is nothing but 1. I have my equation number 5, and from the first equation in equation number 5 I got that the value of this side is 1. So value of minus beta star upon gamma is 1. So minus beta star equals to gamma. Okay, I hope I'm clear. Now from equation number 3 also I can write that delta equals to alpha star. I can write that delta equals to alpha stars. Okay. So finally where I have reached that gamma equals to minus beta star and delta equals to alpha star. See, I've got the value of gamma and delta. So initially I started with the matrix Q, and now here we had alpha and beta. Now I know the value of gamma and the value of delta. So what is the value of gamma and delta? See, the value of gamma is nothing but minus beta star, and the value of delta is alpha star. So here I will put the value of gamma and delta to its respective places, and now I get the matrix this with this unitary condition, because in this matrix includes only alpha and beta. So out of the three equations from equation number 5, I used alpha into alpha star plus beta into beta star is equals to 1. Hence, the matrix involves only three independent quantities. How three? See, alpha is a complex number and beta is alpha star and beta star its conjugate. So, in order to find alpha, I will need two independent quantities, and for beta also, I will need two. But since there is one constraint, alpha star into beta star equals to 1, so I will minus 1. So basically now I have got three independent quantities, and this is the respective matrix. Hence Q involves only three independent quantities which are used to describe the orientation of a rigid body. I hope I'm clear. I know all these things gets difficult to understand, but once you start solving, no, this thing is really simple. See, we considered a linear transformation, then we found out the matrix. Since we are considering rotation, so the matrix is unitary. After seeing that the matrix is unitary, and also that its determinant is 1, I got my equations which gave me the constraints. Now finally, using some equations here and there, I got the value of gamma, which is minus beta star, and delta, which is alpha star, and hence my matrix Q got transformed, and I got in the form of this. So hence the matrix Q involves only three independent quantities which are used to describe the orientation of rigid body. See, the next concept, the next theorem is quite difficult, so we'll take it in the next lecture. And then this is really important theorem. So this also I will complete in the next lecture.